Hello everyone, welcome to the lecture 30 in the course Diffusion in Solids. So today will be the tutorial lecture. We'll solve some problems based on the concentration profiles in interdiffusion zone, Metano-Boltzmann analysis and Kirkendall effect. And like I have said for every other tutorial that please read the problem, but before going into solution, pause and try to see that if you can solve yourself. So the question number 1 is what are the units of Boltzmann parameter? So these are the options, and I hope you remember that the Boltzmann parameter lambda is equal to x by root t, and this x by root t will have the dimension m by root s. Okay. So now moving ahead to question number 2. A binary diffusion couple of two metals A and B is annealed isothermally, and the interdiffusivity and intrinsic diffusivities are determined. When XA is equal to 0.2, the intrinsic diffusivities of A and B are in the ratio 2:1. What will be the ratio of d tilde, which is the interdiffusion coefficient, to dB at this composition? Assume equal local equilibrium of vacancies. So if you utilize what is the Darken's equation, which is d tilde is equal to xa dB plus xb dA. Again, remember that it is xa dB plus xb dA. Do not make the mistake of writing it as xa dA plus xb dB. Otherwise, you will end up in a wrong option. Now, what is given is dA by dB is equal to 2. So, therefore, dA is equal to twice of dB. Now, given is xa is equal to 0.2, so xb should be 1 minus 0.2, which is 0.8. And now, if you substitute this value in this equation, substitute dA as twice of dB, then it is pretty straightforward that you will arrive at d tilde by dB as 9 by 5. So, the correct option is answer B. Moving ahead. Question number 3, which of the following is an assumption of Darken's equation? So, Darken's equation, let us look at the options. That latest vacancies are immobile. That is certainly not an assumption for Darken's analysis. The system is non-isothermal. That is also not true because Darken's equation are analyzed for the interdiffusion scenario where the temperature is constant. Then the system maintains local equilibrium. So, this is assumption that the vacancy are in equilibrium, in thermal equilibrium that is attained. So, that is one of the assumptions of the Darken's equation. The intrinsic diffusion coefficients are equal. That is not true because it actually relates dA and dB to d tilde. So, the correct option is C. Moving forward. Which of the following observations can be attributed to the Kirkendall effect? So, let us look at the options. Movement of the inert markers due to unequal diffusion rates. Yes, this option is correct. That is how, if the diffusivities were equal, then we would not have observed the movement of inert markers. So, this is what Kirkendall showed. Formation of Kirkendall voids in a diffusion couple, this is also correct. We have seen this that there is voids forming because of the effect of unequal diffusivities. Equal flux of atoms in opposite directions, as of it is indicated here, the flux is actually not equal. You have this difference in flux itself causes the formation of the vacancies. So, this C is not a correct option. D, evidence of vacancy mediated diffusion, which is correct because this Kirkendall effect established that the diffusion rates are unequal, which is only possible when you have a vacancy mediated mechanism. So, the option A, B and D are correct. Remember, in the assignments and later in the exams also, you will have such questions where there are multiple options correct, and you have to mark all the correct options in order to secure the full marks. Moving on to question number 5. So refer to the diffusion couple and the concentration profiles below. So here, if T2 is equal to T1, then the ratio X2 by X1 is equal to. So you see that what we are talking about in this, this is a diffusion couple Cb minus and Cb plus. After annealing at some temperature and time t equal to T1, the interdiffusion zone thickness is this, and which becomes larger when you anneal for a longer time. And this is the composition profile at T1, this is at T2. So what is given here, what are T1 and T2 and X1 and X2 here given as that there is a composition Cb star. At time T1, the composition plane is located at a distance x1, and at time T2 it is located at x2. Now we are given the ratio of T2 is by T1 which is 2. Now we have to find out what is x2 by x1. So this we saw that the definition of the Boltzmann parameters itself, it told us that during interdiffusion any composition moves such that x1 by root T1 is equal to x2 by root T2. This is measured from the metano plane. So this implies that x1 by root T1 is equal to x2 by root T2. So therefore, since we are given that T2 is twice of T1, so we get x2 by x1 as root 2, which is equal to 1.41. So the correct option in this case is B. Okay. So then let us go to the question number 6. So a diffusion couple is formed between nickel and tin and annealed at 230 degrees centigrade for 200 hours. The interdiffusion zone consists of nickel solid solution, Ni3SN, Ni3SN2 and Ni3SN4 equilibrium phases and a metastable NiSN4 phase. Sketch the composition profile assuming equal thickness of all the phases formed. So if you look at the nickel tin phase diagram, you see that there is a Ni3SN, Ni3SN2, Ni3SN4, and there is a nickel solid solution also, but there is no NiSN4. That is the reason why it is a metastable phase. This again is a very useful application of the diffusion couple or the interdiffusion technique, where such metastable phases, if they are properly analyzed, their structures and all, you can get the information about the metastable phases through diffusion couple experiments. So it need not be the case that all the equilibrium phases are present in the interdiffusion zone. Sometimes you can get certain metastable phases which are formed because kinetically it is easier to form. So now what we are given is that these are the phases that are formed in the interdiffusion zone. So you please pay attention here that when you are plotting the composition profile, let's say if you are plotting either with XNI or XSN, make sure that you go in the correct order of the composition. So you see that nickel solid solution means there is 0 tin. Ni3SN, then the tin is 25 atomic percent, then it increases further in Ni3SN2, further in Ni3SN4. And you will see that here when it is a solid solution at 230 degrees centigrade, there is a slight gradient. Okay, but when it comes to Ni3SN or Ni3SN4, Ni3SN2, you have a relatively narrow range. Although Ni3SN4 is something which sometimes gives a horizontal profile, but potentially it can also give you a slight gradient. But for the sake of analysis or easier understanding, we have kept it horizontal. But if you draw a slight gradient also, it is okay. And then NiSN4, please pay attention here that it's a metastable NiSN4 phase. Now NiSN4 has highest amount of tin. So you should draw NiSN4 closest to the tin. If you draw NiSN4 somewhere here, then it would be wrong, because NiSN4 will grow very near to the tin. So that's how in the sequence you have to follow. So based on the composition of tin, you sketch these profiles in the increasing order. In this case, you could also sketch, if it is written composition profile, you can as well draw a nickel profile also. That is perfectly acceptable, but the order of the phases should remain like this. So moving on to the next question. Which of the following statements generally hold true about self-diffusion coefficient, intrinsic diffusion coefficient, and tracer diffusion coefficient for any element diffusing through vacancy mechanism? So see, last class we talked about the different definition of the diffusion, various diffusion coefficients. So the self is equal to d star is equal to di. This is not true. The self diffusion coefficient, as we described, it is actually the diffusion which is taking place without any driving force, a atom diffusing inside a pure metal or in an alloy of AB. Also, the intrinsic is when the movement of A occurs due in the presence of a chemical driving force. So they are not equal. The second option, D star is equal to F into D self, where F is the correlation factor. This is the correct relation. Because of the correlation factor, because of the probability of reverse jump being higher in the vacancy mechanism, because the vacancy is next available next to the atom after it has made a jump. So therefore you have this correlation factor. So therefore the D star or the tracer diffusion is equal to F into D self, where F is correlation factor. Similarly, last lecture we saw that the intrinsic diffusion coefficient is equal to D star into phi, where phi is the thermodynamic factor, and this also holds true. So this is also correct relation, and therefore D star is equal to Di into phi is not correct. The correct form is this. So the answers are B and C. Now coming to question number 8. Suppose a diffusion couple is formed between elements A and B and annealed at high temperature T. Only intermetallic phase A3B grows in the interdiffusion zone, and A3B is a line compound. Can we determine interdiffusion coefficient for this diffusion couple using Metano-Boltzmann analysis? If not, why? See, if you look at the Metano-Boltzmann analysis, it gives us the interdiffusion coefficient d tilde as minus 1 by 2t dCb by dx at a particular composition Cb star of our interest, integral Cb minus 2 Cb star x into dCb. Now, you see that if according to the given description, if you sketch the composition profile, it would look something like this. So you have A and B, and only A3B, this phase grows in the interdiffusion zone, which is a line compound. Now, because it's a line compound, you will not have any gradient. Actually, even if it was a slightly wider compound, the gradients will be extremely small. So in any way, in this case, it is purely horizontal. What it means is that if you try to calculate the dCb by dx, which is the slope of this profile at any composition, it is 0. Okay, it's a horizontal line, so the composition, the gradient is 0 at any given point. So therefore, it will lead to d tilde being infinity, which is not physically possible. So in such cases where you have these intermetallic phases growing, this Metano-Boltzmann analysis through this formula, you cannot calculate d tilde. So what basically is done is to try and come to an average kind of a diffusion coefficient. So what you define is something called as integrated diffusivities, or in some cases average diffusivities, but the discussion of them is beyond the scope of this particular course, but you can refer to the book that is mentioned as the reference there. It is explained in even greater detail that what is this integrated diffusivities mean and how they are calculated. But as far as this question is concerned, so if you try to calculate this dCB by dx for such profile, it will be 0, and therefore this entire thing will go to infinity. So the next question, aluminum magnesium diffusion couple is annealed at 420 degrees centigrade. The phase diagram and the composition profile is shown below, and you have to identify the phases in the composition profile. So this is the magnesium aluminum phase diagram, and these are the composition profile that is given. The blue color is magnesium, and the brown color is aluminum. So what actually you should see here is that you have solid solution on both the sides. So you have therefore this kind of gradients which are forming. You also have this gradient. Now you will say there is only two solid solutions. So why is this gradient? This gradient is perhaps reflective of a intermediate phase which has a wider composition range, which is in this case is gamma. So most likely this corresponds to gamma. And then there is a horizontal portion which should correspond to an intermetallic phase which is a line compound or has a very narrow stability range. So such a phase is a beta phase in this diagram. So if you see, this is beta, this is gamma. So then next to beta, the solid solution is aluminum, and next to gamma, here the solid solution is magnesium solid solution, and then the small horizontal portion should indicate the end members. So therefore you can identify this is magnesium, then this is magnesium solid solution indicated with brackets, then this is the gamma phase, beta phase, again aluminum solid solution, and then pure aluminum. So again give an important consideration for the order. You should not make it reverse, because this is a magnesium solid solution, of course will occur on the magnesium rich side. So this is how the phases can be correctly identified. Now coming to the last question of the tutorial, it is determined by the experiment that Kirkendall markers placed at the interface of a diffusion couple formed by welding a thin plate of metal A to a similar plate of metal B move with the velocity of 4.5 into 10 power minus 12 meter per second towards the A component, when the concentration XA is equal to 0.38 and the concentration gradient dXA by dx is 2.5 into 10 power 2 per meter. The chemical diffusion coefficient or interdiffusion coefficient d tilde under these conditions is 3.25 into 10 power minus 14 meter square per second. Determine the values of intrinsic diffusivities of these two components. Now see, if you remember the Darkins relation, in the Darkins relation you have d tilde is equal to XA dB plus XB dA. But so in this question you are given d tilde, you are given XA and XB, but you don't know dB and dA both. So how do you determine then? So there is something else given, which is the velocity of the Kirkendall marker plane. Now can we relate the velocity to these intrinsic diffusivities? What we have seen in the previous lecture is this expression, Vk is equal to minus Ja into Va bar minus Jb into Vb bar. Here Vk is the velocity of the Kirkendall marker plane, VA bar and VB bar are the partial molar volumes of A and B, and JA and JB represents the intrinsic diffusion flux. Now, this relation is between V and J. Can we convert it into the relation between V and dA, because D is A and dB, because this is what is given to us in the problem. So, Vk, we can write, we can replace Ja as dA minus dA dou CA by dou x at the Kirkendall marker plane. So, this minus goes off into Va bar plus dB into dou CB by dou x at again the Kirkendall marker plane into Vb bar. Remember here this Va and Vb are the volumes. So, this Vk is equal to dA. So, this dou Ca by dou x can be written as minus Vb bar by Va into dou Cb by dou x. This we have seen previously, multiplied by Va bar plus dou Cb by dou x at Kirkendall marker plane into Vb bar. So, then this Va and so Va bar and Va bar will get cancelled. What you have is minus dA into Vb bar into dou Cb by dou x plus dB into dou Cb by dou x into Vb bar. So, if you take Vb bar into dou Cb by dou x at k common, you get Vk is equal to minus dA into dou xb by dou x at k plus dB into dou xb by dou x at k. How do you get from here to here is the assumption that Va bar is equal to Vb bar is equal to Vm. So, the partial molar volumes are equal, and they therefore they are written as Vm, and we know that Xb is equal to Cb times Vm. So, this essentially the product Cb into Vm can be written as Xb. So, therefore, we get this relation Vk is equal to dB minus dA into dou xb by dou x at the Kirkendall marker plane. So, if you want to express in terms of Xa, you can write Vk is equal to dA minus dB into dou Xa by dou x at Kirkendall marker plane. So, now we have this relation. So, let us utilize this. So, we are given Vk is equal to 4.5 into 10 power minus 12 meter per second. Xa is given as 0.38, and dou Xa by dou x is given as 2.5 into 10 to the power 2 per meter. The interdiffusion coefficient is given as 3.25 into 10 power minus 14 meters per meter square per second. Please remember, in this case all the units are okay, but pay careful attention in assignments or in the exam for the units. If the units all should be in the same units should be there, otherwise your answers may come wrong. So, this d tilde is equal to Xa dB plus Xb dA. This is the Dawkins relation. So, if you put then you get this equation 1, which is 3.25 into 10 power minus 14 is equal to 0.38 into dB plus 0.62 into dA. Now, there are two unknowns. So, we need another equation. So, that is where we will use the relation Vk is equal to dA minus dB into dou Xa by dou x. So, here dA minus dB is equal to Vk divided by dou Xa by dou x. So, we are given these two quantities, and if you calculate, then you get 1.8 into 10 power minus 14. So, therefore, the dA is equal to dB plus 1.8 into 10 power minus 14. So, now if this dA you substitute in the equation 1, what you get is 3.25 into 10 power minus 14 is equal to 0.38 dB plus 0.62 into dB plus 1.8 10 power minus 14. Some rearrangement if you do, you get dB is equal to 2.134 into 10 power minus 14 meters square per second, and dA is equal to 3.9 into 10 power minus 14 meters square per second. Okay. So these are the values that you can obtain as the intrinsic diffusivities for these two elements. So with this, we'll end this week's tutorial and the lectures, and the next week onwards, we'll take up the computational thermodynamics and kinetics module. Thank you.